That's not good. Well, so we got notes today, and chapter 4. We're actually talking about 3 sections today: 4:1, 4:2, and 4:3. They are all tied together. That's why we're doing them all one shot here. And so let me just kind of give you an idea of what's happening. Tuesday is the next day you have class. I have class, actually. Teachers are required to take a class on personalized learning, so I will be in class all day on Tuesday. So you will have a sub, which I'm assuming will know nothing about calculus. So I'm going to give you this assignment. It's going to be long, but you're going to have the entire period on Tuesday to work on it. And so my hope is, don't come in Tuesday with nothing started. So you should start it. My hope is, just like with related rates, that you're going to get so much time that by the end of the period on Tuesday, you will have corrected it and understand every problem and know how to do them all by helping each other out. Got it? And I think you're going to get some work. You should be able to get work time today too. These notes will take a while, but it won't take an hour or so to do. Okay, now 4:1 and 4:2 and 4:3, they're all tied together, and I'm going to give you notes that just kind of think about all 3 sections together. It just makes more sense to me that way than trying to break it up the way they did. So just kind of picture that in your head. And these are all, I would say, graphing applications. Of the derivative. So if you remember, we are in a unit on applications of derivatives. Related rates obviously is a good application of derivatives, and so this is going to be another application of derivatives, looking at how it can help you find different features of a graph of a function, or graph of a curve or equation. So we have these 2 things they're called tests, but they're more procedures, I would say. The first derivative test and the second derivative test, which basically just saying all the stuff the first derivative can help you find on a graph, and we call that the first derivative test, and then all the stuff the second derivative can help you find on a graph, we're going to call that the second derivative test. Alright, so we're going to start with the first derivative test. Okay, and so this is going to be used to find extreme values. And by extreme values on a graph, we mean maximums and minimums. We've talked about this already, right? You've had to find the maximum value. And how would you find that using the derivative already? Slope is what? 0, right? And the slope is the first derivative, so you can see how that's going to work out. Eventually that's supposed to get quiet, but it still feels like it's going to explode any minute. If it doesn't bother you as much as it bothers me. So maxes and mins, we're going to be able to find first derivative like we have before. We kind of get an idea of that already. Increasing and decreasing. And we've talked about that already too. What does the word increasing mean? What's positive? Slope is positive. The slope is also known as the derivative, right? So you can see how the first derivative is going to help there. If the first derivative is positively increasing, the first derivative is negatively decreasing. And critical points. Let's write that out, and we'll talk about what those are. Okay? So anywhere on the homework, if it says to you, find a maximum, find a minimum, find the local maxes or absolute maxes, or where it's increasing or where it's decreasing, or critical points, all of it's just saying, hey, go ahead and use the first derivative test to help you find that. All right, so let's walk through how it will work. First, let's show you a graph. Here's an endpoint. All right, so let's take a look at that. Let's start right here. He goes up and comes down. We think about that. If you didn't see anywhere else on the graph, you just saw that, you think of that as a maximum, right? Of course, that's not the highest point on the graph, but it's still a maximum. And we call that a local maximum or a relative maximum. Or relative. It's relative to its area or its position, in other words. So if they say find local maxes or mins, the local max is just a point like that. This would be a local minimum right here. And what did we already say? What is occurring at that point? How do you know that's going to happen? You bet. Slope is 0, so the derivative is equal to 0. Derivative there is equal to 0. And of course here too, this is a local minimum. Besides being a local minimum, what else do you notice about that? Yeah, it is, right? So that is the absolute minimum we say. In other words, that is the minimum value. So it's also the absolute minimum. So, local mins and maxes are where the first derivative is equal to 0, but not just that, it has to go up and then come back down, or go down and come back up. So we're going to talk about that in more detail. It's not just where it's equal to 0, because you could have other situations we'll just show you. Absolute would be the absolute highest or the absolute minimum value. Where's the absolute maximum here? So this endpoint, right? And notice that doesn't have to be where the derivative is equal to 0. It's just the only, the place where it is the highest value. But if you think about it, it would have to occur either at an endpoint or a place where the graph is turning around. That's the only possible way you could have an absolute max or min. Okay? So, let's go through each one of the things that I mentioned up there, and keep this in mind here. Let's start with critical point. On the homework, it's going to ask you to find the critical point or critical points. And critical points are just simply places where the first derivative is equal to 0 or does not exist. And these are possible. Mins and maxes. They don't have to be, but they're possible. So we already know, obviously, there's a critical point right there. How about does not exist, though? What would that look like in terms of a graph? Remember what how do you tell? Yeah, say it again. Cusp. Very good. So this is f prime of x equals 0, but that's f prime of x does not exist. Is that a local max, do you think? It is. That's a local max too. Now, all places where the first derivative is equal to 0 are not maxes and mins, though, but they are critical points. So both of those are critical points. A critical point, but not max. And by max, I mean, when we just say a maximum or minimum, we mean local or relative, okay, not the. If you want the absolute, they will say the absolute. Otherwise, say find the max and mins, they mean all the local ones. So this could happen. You could have a graph that comes up and it plateaus and then it goes again. So right here you have f prime of x is equal to 0. That's a critical point, but that's not a max or min. And that can happen. And you can have a graph where you have a vertical tangent. It's kind of unusual, but right there, f prime of x, it does not exist. That's a critical point, but that's not a max or min. Yeah?
What kind of equation would produce that kind of graph?
It's pretty funky, isn't it?
Yeah.
Yeah. And sometimes I'll find an example of one. It's really unusual, rare. If you think about, thank you, it's like x cubed, goes like this, and it's 0 right there, but the cube root of x would go like, you know what I'm saying, the other way. That would be an example of that. Make sense? I think that would go, because it would go sideways. You know what I'm saying? X equals the cube root of y, I should say. I think that's what it was. Or the inverse of that. If you get that, you know what I'm saying? You get the idea of what I'm talking about. So, okay, critical points. Got it? Sometimes mins and maxes, not always. All right. The other thing we said, increasing, decreasing. We'll make sure we get this down here. Increasing. This is where f prime of x is greater than 0. Decreasing, just simply where you have the negative derivative. And what else did we say? Okay, so what is a minimum and what is a maximum? Let's define that. So we know it has to be where the first derivative is equal to 0 or does not exist, but that's not enough. So maximum, the definition of a maximum is where the first derivative equals 0 or does not exist, and what else would be true? How do we know that's a maximum and not just a place where, thank you, is that a bonus check or is it? What makes that a maximum? What would you say? How do you know for sure that's a maximum? What do you think, Luke?
Increasing on the left, decreasing on the right.
Perfect. So, and you can use those terms, increasing before this x value and decreasing, a lot of ands there, but you get the idea, decreasing after. And instead of using the words increasing and decreasing, how can we use those with calculus symbols instead? Oh, we don't want to use limits. What does increasing mean? F prime of x is greater than 0. So instead of you saying increasing, I could say f prime of x is greater than 0 before, and f prime of x is less than 0 after. So all this together helps you decide whether or not it's a maximum or minimum. So that would be a maximum. I did write maximum, didn't I? And of course, minimum, same story here. F prime of x equals 0 or does not exist. And f prime of x would have to be negative before and positive after. Okay? Alright, let's go through an example of going through the whole deal and show you how it would work to find all of this stuff they're looking for. Some problems they'll ask you just to find some of them, some problems they'll ask you to find everything. But we're going to find everything in this one here. So f of x is equal to x cubed minus 3x squared plus 2. We're going to do the first derivative test. So we're going to take the first derivative. And the first thing I want to do is I want to find critical points. So how am I going to find critical points? What's a critical point? Slope is 0 or does not exist. So how am I going to find critical points? Well, maybe it's too obvious. Maybe I'm insulting your intelligence. I would take the derivative and set it equal to 0 or does not exist. So to find critical points, you're going to take 3x squared minus 6x and set it equal to 0 and solve. And 3x squared minus 6x equals does not exist in a solve. Kind of. Can't really set something to equal that does not exist. But are there any values that you can't put in for x here, in other words? No. So they're down here. There aren't any. How about over here? Yes, we would factor and solve. You bet. I would take out a 3x, x minus 2. I would solve, and I get x equals 0, x equals 2. Those are my two critical points right here. Those are the x values. If I had to actually find the points, if it said actual points, not just the x values, how would I find the y values? The original one. Very good. All right, everybody gets that? Beautiful. All right, so they might just say, find critical points and you're done. That would be it. That would be nice. They might say, find where it's increasing and decreasing. So now I'm going to take the work I just did to get the critical points and use that to be able to figure out where the derivative is positive or negative. So we have our derivative, f prime of x is equal to 3x squared minus 6x. I take my critical points, and what I want you to do is to make a number line, or a chart, or a table, or whatever you want to call it. Okay, so we're going to make a little table or chart for f prime. Think of this as a number line, and we're going to put on our number line our critical points. So we had the point 0, x is 0, and x is 2. I know that the slope is equal to 0 there, and some people like to even put a little 0. Sometimes in the books you'll see like little zeros there. I usually don't write anything at all. But I know that's where it's 0. That's where the slope is changing, most likely. It could potentially change. It doesn't have to. Now I want to find out what's going on in these intervals here. Is it positive or negative? So to the left of 0, I just take a value, -1, and I put it into my derivative. -1 squared is 1, 3 plus 6. I get a positive value. It doesn't really matter what I get. I get 9, but I don't really care what I get. I get positive. That means everything in this entire interval is positive. Why can I get away with only checking one value in that entire interval? Yeah. Well, go ahead. You're going to ask a question? Or? Okay, how can I get away with only checking one value in that entire interval?
Because it only goes up or down. It can't switch off. -2 can't be different than -1 because otherwise it'd be another local minimum.
Yeah, okay. Does that make sense? Now you know what I'm saying? The only way that it can come back up is if there was another 0 or it does not exist. So you know for a fact it has to be doing the same thing the entire way. Otherwise you would have found that it turned around again. Okay? So that's how you can just check one. So check one here. Plug in another number. Doesn't matter which one. Plug in 1. 1, 3, minus 6. So that's negative. Now let me ask you a question. Do I even need to check this one? Do I know it's going to go up for sure? No, I don't know if it's going to go up for sure. Could it go down here? It certainly could go down. It could go like this, flatten out, and go down again, right? It can do that. So don't just start thinking, oh, I don't need to. This one went up, this is going down, this one up. You got to check them all. You have to check them all. Even though most times it does go up, but it doesn't always. So put in something bigger than 2, like a billion. I don't know if that helps you, or maybe even something that's smaller, but it's like 10. So that would be 100, 300, minus, definitely positive, right? So it's going up. So now I got to answer the question. You can't. That's not good enough to answer the question. You can't just take your table and say I'm done. I need to answer the question. The question was, where was it increasing? And they are going to say why on the AP test often. So where is this increasing? Now f prime is less than 0. These are x values here. Let's use interval notation. So from what to what is it increasing?
Negative infinity to 0.
Yes, negative infinity to 0. Do I put a square or around parentheses on infinity? Parentheses, never square, right? What about at 0? What do you think? Square or round?
Right. Square.
Round, because it doesn't. It's the slope is 0 at 0.
Slope is 0, 0, right? It's not, yeah. So, and you'll have different people actually argue that, even mathematicians, so they don't really take out one way or the other, because there is some dissenting argument about that. But anyway, negative infinity to 0, and, you can use that symbol or write the word and, union, it doesn't really matter, from 2 to infinity. That's increasing. Why? Because the derivative, all you guys tell them if they ask why, because the derivative is greater than 0, it's positive. And then we got decreasing. And that's between 0 and 2, of course. Why? Because f prime of x is less than 0. So they might say find critical points, you'd stop there. They might say increasing, decreasing. You have to find the critical points in order to find increasing, decreasing. Even though they won't say find the critical points. So we did that. And they also might ask you to do all of it or just part of it. They might ask you find the local maxes and mins. And you'd have to do all this work anyway to find the local max and mins, really. But we really don't have to do too much more work. We got our table here. This is going to tell us, where do I have a local maximum? Yeah, at x equals 0. So I have a local maximum, or relative maximum, at x equals 0. And if they said at what x value, that would be fine. But usually they say, what is the local maximum? Is the local maximum 0? Yeah, maximum and minimum values are not x values. Make a note of that. They're y values. So if it says, where does it occur at what x value, I'm fine. But if it says, what is the local max, that means, what is the y value? And how would I find the y value at 0? The which one? The original equation. 0 minus 0 plus 2, I get 2. So that's the local maximum value. And the local minimum value that was, and we can tell here, it's at 2. And the local min is when y is equal to. So we put 2 in, and we figure out what that is. 2 cubed is 8 minus 12, right? Negative 4 plus 2, negative 2, it looks like. And they're going to say y. And you have to justify y. Why is this a local maximum?
That's when
When the derivative is 0 and, because that's not good enough, right? Why else is it a local maximum?
the highest y value.
Excellent. Everybody hear that? That is exactly how you describe it. F prime is greater than or equal to 0 before, greater than 0 before, and less than 0 after. Or f of x is increasing before and decreasing after. Don't say f prime of x is increasing. That's a major mistake. What would f prime of x is increasing mean?
F double prime.
Yes, because increasing means the derivative. So you say f prime is increasing, you actually mean the derivative of f prime is positive. You're saying the second derivative is positive. And we want to say that. At least not at this point. Okay, we're going to get to that in a moment. Second derivative test. Okay, now one last thing. If they said to you absolute max or min, then you got to just be careful. Make sure that you check the endpoints. There weren't any endpoints in this thing here, in this one, okay? Because it went on forever, there's no endpoints. So if you can look at the shape of the graph, then you would know. So let me give you some kind of situations here. Obviously, if this endpoint, we already did one like that, is higher, you know, this is the absolute max here. But this is the absolute min here. So you have to always compare these maxes and mins, because that's local, to the endpoints and see if they're higher or not, or lower, depending on what you're looking for. Is there an absolute max there? No, right? That's obvious. Is there an absolute min here? Yeah, you bet. So this is absolute min. No absolute max. Is there an absolute max there? What's the absolute maximum value? What did you say? Okay, but now we're saying no as an approach. We're saying what is the highest value? What's the maximum value?
4.
Well, that's a whole. There's no point at 4. Don't say
That was a
that.
trick question.
Yeah, don't tell me the number before 4, because what's the number before 4?
3.8.
Is there an absolute maximum?
No.
No. Isn't that weird? There's no absolute maximum here. There's an absolute minimum, of course, and no absolute maximum. Because there's no endpoint on that. All right. That's the first one. Yeah.
So if you had a sine graph, would you have any absolute maximums or minimums?
Okay. Yeah. Well, that's a good question. So in other words, you're wondering. That's 1, right? So you're thinking, well, there's a lot of places. So is there an absolute max? Yeah, there is. What's the absolute maximum? 1. Because remember, maximums are y values. Doesn't matter. It doesn't matter how many times you hit the maximum. It is the maximum value. If they say, what's the absolute maximum value? Don't forget that's a y value. They're not asking you where does it occur. They say, what is it? It's 1. If they say, for what x values does it have an absolute maximum, you could have multiple. And then maybe, yeah, you would have to say, 2k plus pi or whatever, something like that. Yeah. Okay? First derivative test. Exciting?
Yeah.
Critical points, increasing, decreasing, maxes and mins. All that stuff can be found on first derivative test. Don't forget, it's not just where the derivative is equal to 0. It's also where the derivative does not exist. You're going to forget this. You're going to go through all these problems and you're never going to have a place where it does not exist. And all of a sudden you're going to get one where you end up with a variable in the denominator, x in the denominator. So there's going to be places where it does not exist and you're going to forget to look for that. And you're going to not get all the critical points. Yeah?
So in that last graph, would that be does not exist critical point? That one that has a hole?
No, we're talking about not where the function is not continuous, we're talking about where the derivative does not exist.
Okay.
So, by the way, a critical point is only a place where there is actually a point. So if the derivative does not exist and the function doesn't exist, there's a hole in it, that's not a critical point because there's no point there. You following me? Critical points are only actual points. All right, beautiful. Let's talk second derivative test. So, this is used to find concavity. Concavity and inflection points. So first of all, I'm not sure if we ever mentioned this in here, the term concavity, what I mean by that. Concave means to cave, the dent in, like a cave in. So concavity talks about where the concavity or how it's concave. This is concave down. This is concave up. This is a smiley face. See that part there, from there to there? That's concave up. This is a frowny face. From there to there, that's concave down. Where it changes concavity, guess what we call that?
Point of inflection.
Yeah, this is a point of inflection or inflection point. So the definition of inflection point is where it changes concavity. So where the graph changes concavity. Oops. That's an inflection point. So we just said it's the second derivative that tells us concavity. So f prime of x, if that is positive, greater than 0, in other words it's positive, well, that's happy, right, if it's positive, so we have a smiley face, concave up. If the second derivative is negative, then it's a frowny face. That's concave down. Just like when you study quadratics and the number in front. If it was positive, it was a smiley face. If it was negative, it was a frowny face. Okay? So, what's going to be happening in the point of inflection, do you think? You bet. So, if it equals 0 or does not exist, that is a possible point of inflection. Doesn't have to be. It only is if it actually changes concavity. You can have a situation where it goes concave up, then 0, then concave up again. It doesn't change concavity, so it is not a point of inflection. Okay? You following me? In other words, point of inflection. But y equals x to the fourth. This is a great example. Draw that too well. Interesting enough, the second derivative at 0 right there is equal to 0. But this doesn't change concavity. It's concave up and then concave up again. That's not a point of inflection. Okay, it doesn't change concavity. So just like when we did the first derivative test and checked for going up and down, increasing, decreasing, we're going to do the same thing here for concavity. Here are other not points of inflection. You can have graphs like this. So this is second derivative. You're going to find out, let's say the second derivative there does not exist. The first derivative doesn't exist, so the second derivative does not exist. But it's concave up, and then it's concave up again. By the way, it doesn't have to, just kind of as a side note here, this always throws people off. Your graph doesn't have to make a smiley face to be concave up. It doesn't have to like come back up this side of the mouth. You following me? This is concave up here the whole time. It's the curvature of the line. It doesn't have to like swoop back up again to be concave up. This is concave down.
What would like a parabola on its side be?
Something like that?
Yeah.
Yeah, so this is a little tricky. First of all, it's not a function, so it's kind of interesting, you know what I'm saying? But we will work with different curves like that, so it's okay. So since it's not a function, this is concave down here, and that's concave up here. So it's odd or unusual, but only because it's not a function that could occur. Okay, let's go through an example with a second derivative test. So this is the exact same equation. We already found the first derivative, which is 3x squared minus 6x. And now we're going to find the second derivative, 6x minus 6. So when we took the first derivative, set equal to 0, we called those critical points. When you take the second derivative set equal to 0, there really technically isn't like an official name for that. Some books will call it critical points for the second derivative. Other books will say possible points of inflection. You see that probably more than anywhere. So we're going to find possible points of inflection. And then we're going to check to see if they really are. So the only way it even has a chance of being a point of inflection is if the second derivative is equal to 0 or does not exist. And we're going to do that. We're going to set it equal to 0 and does not exist. So 6x minus 6 equals 0 or 6x minus 6 equals does not exist. Let's start with this one over here. Is there any value you can't put in for x? Is there anything that's going to make that does not exist? No. So there's nothing over here. Forget about that. Here we would solve and you're going to get 1. So there's your x value that is a possible point of inflection. Now we're going to check to see if it is. We're going to find concavity here. We're going to make a table for the second derivative. making these tables, you must label the table. They make a very major point of that. So they consider it no work at all if it's not labeled because they have no idea what it is. So if it's a first derivative or a second derivative, make sure you label first or second derivative, whatever is going on there. We write down our critical point, which is 1. We test values on either side. Same idea. You only need to test one number.
0.
Yeah, 0 would be good. We put it into the second derivative, not the first derivative. We're checking concavity here. So we put 0 into the second derivative and we get -6. So this is negative. That means it's concave down. And make a little mark because it's showing that it's concave down there. Then I put in a number bigger than 1, like 1,000,000, and I get 6,000,000 minus 6, so it's positive. So we'll answer the question. This is concave up when from -infinity to 1. And they're going to say why, or justify. And why is it concave up there? Ooh.
Down.
I just seen if you're paying attention. Thank you. Pass the test. It's concave down. Job. Why is it concave down there? There's one simple reason. F double prime is less than 0 or negative. You can say negative if you want. Perfect. That's the only reason why. Simple reason. And it's concave up from 1 to infinity because the second derivative is positive. It's greater than 0. And we say find the points of inflection. We don't have to do really any work anymore on that because we look at our table. This is why the table is so important. Make this table every time. Any points of inflection? Yeah, what is the point of inflection? X equals 1. That's not really a point. We got to make sure it's a point in our original equation. Just because it changes, remember, it has to be a point there. So we put 1, what are we going to do with 1? Very original equation. 1 minus 3 is -2 plus 2, you get 0. So the point of inflection is 1, 0. Why?
Between the two concaves.
Changes concavity, right? Is that, you know what I'm saying? So you can say that it changed concavity there, or you can say because f double prime of 1 equals 0, and f double prime of x is less, it was down right before, less than 0 before, and f double prime of x is greater than 0 after. Just because it changes concavity does not mean it's a point of inflection. So just a kind of final word on that. Let's say you have an asymptote here. It's pretty common, something like that. Concave down, concave up. There's no point here. It changed concavity, but there's no point here. This is not a point of inflection. Has to be an actual point to be a point of inflection. So that's the first derivative test, the second derivative in a nutshell, and that's all of 1, 4, 1, 2, and 3. 3 just ties it all together. So here we go. They say take everything you just did and graph it. So in the land of calculus before graphing calculators, this was actually pretty cool that you could do all this stuff and quickly get a graph of some seemingly difficult things to graph. This one, let's see what we're dealing with here. So we're going to tie it all together. We're going to make a graph. We'll take all the values we just found and plot them on here, and we're going to get a pretty good, quick sketch of what's happening. What do you want to start with? Let's get some kind of scale on here. You guys here, we're going to try to offer class next year, doesn't matter as you got, but we're going to try and do advanced algebra and pre-calc in 1 year. Think that's a good idea?
Except don't do it because then I'd be jealous.
Oh,
Except don't.
well, maybe you'll pave the way for somebody else. We'll see how it goes. I know Memorial's been doing it for like 30 years, so
So what do they do? Do they just have a lot more kids end up in Calc?
they have way less than we get.
So how are they benefiting from it then as well?
They don't let many kids take algebra in 8th grade.
Oh, so then.
So I'm talking about like Memorial, Madison schools a lot of times, yeah. So and then they don't offer like you guys Calc BC after pre-calc. You got to do AB and then you got to do BC. And we're actually going to change that sequence around a little bit too if we do this. So yeah, they don't have the numbers that we
So
have.
then you'd go geometry to pre-calc or algebra to pre-calc.
And then you could do with that. So what we're thinking is we're looking at I don't know, we're looking at different options. We'll see. It doesn't matter to you guys, you're all past that anyway. Alright, so tell me what do I know for sure? Let's start with first derivative test. What did I find in the first derivative test? Give me some points to plug in here. What do I got? Critical points. Where are my critical points?
0 and x equals 2.
Alright, and I think we found the y value, right?
Yeah.
So we had 0 and 2. When I put in 0, what did I get? Was it 2? The point 02 was a maximum, correct? I know for sure that's going to go like that.
Yeah.
And at point 2, negative 2, if I remember right, was a minimum. I know that's going to go like that.
Was it 2 negative 12? Well, I'm just.
Maybe I'm wrong. I could be wrong. Help me out.
No, it's 2 negative 2.
Was it negative 2?
It is negative 2. Yeah.
Okay. So I had that point, and then I had another important point, the point of inflection, and that was at 1, 0, if I remember right. Then I also look at my tables. I have my tables, and I can sketch in that the fact that it was increasing here was going up, and then it was going down, in between here, and then it was going up. So I kind of lightly sketch that in, maybe with a pencil. So for my tables, I know up, down, up. For my second derivative table, I know it went concave down and then concave up. So from that information, then I can roughly sketch in, okay, I'm going to go concave, so I'm going to do a frowny face here until I get to this point, but I got to go through here, I'm going to go down. And I'm going to do a smiley face here, I got to get into this point here, and then I'm going to go up. Now I could find out more precisely where it's crossing the x-axis if I wanted to, but overall that's a pretty quick graph of a fairly complicated, thing you had to do before, where you might have to complete the square and factor and all that stuff to be able to get an idea. Now you can sketch things out fairly quickly that way. If there were asymptotes, you would put those asymptotes in. How do we find asymptotes again? A vertical asymptote. Now, is it always when you get 0 in the denominator? What do you got to be careful of? So you don't want 0 in the denominator, but remember, this could be a whole or it could be a vertical asymptote. And how do we figure out the difference between a whole and a vertical asymptote? Factored, right? So we factored. Yeah, we used limits, but you're right. So we factored and we canceled, and whatever was left, anything canceled out was a whole. Anything left was a vertical asymptote. So don't forget all that stuff you've done too. All right, beautiful. Let's do some problems. I was going to have you get up and do some on the board to practice. You want to just do them right where you are, or what are you thinking? You just want to start your homework? You want to do some practice? You want to move around? You want to just get going, huh? All right. Don't complain when you see how big it is, alright?
Oh, it's so big, I hate it.
Oh, God, it's already.
The page number's too big.
The page number.
Let's see if I can write a faster way.
Bigger.
Oh, no. Oh, I two, three.
It just fills up that whole box.
It's like only 5,000.
I crossed a few off, so.
17,
Crossed a few off.
300.
Alright, this is your homework.
Oh, okay.
Otherwise, just die.
I told you not to complain.
That's all right. They could be really short.
30 problems. Just think of it as, 1 through 30 all on an Algebra 1 assignment.
6 axes.
Now you want to do all the stuff we just did on every problem, so don't panic about that. But
Oh, I thought you just said we did have to.
no. You won't have to. If you kind of look at the way they set up, the first section is more or less the first derivative test. The second one is more or less the second derivative test. The third is kind of graphing it stuff out together. But just do the what they ask for, increasing, decreasing, whatever part.
Do you,
7, 9, 13, 15, of course we know that.
I was gonna send the homework to Charlie. Is it?
I'm gonna post it to my
We're gonna
website,
post it?
the video. So
Alright. You're gonna have that on the video?
I'm gonna try to do that right now. Yeah.
It's either him asking me